The universe could well be nearly twice as old as the widely accepted 13.797 billion years. The extraordinary contention in a recent paper by University of Ottawa Professor Rajendra Gupta has the potential to upend much of what we have come to accept about the age of the universe. What triggered Professor Gupta's study was some profoundly puzzling discoveries by NASA's James Webb Space Telescope. Two in particular threw off the astrophysics community a star named Methuselah, which is at least a billion years older than the universe, and several fully mature galaxies within barely 300 million years of the Big Bang. In other words, what should have taken billions of years of cosmic evolution was evident in these galaxies so soon after the Big Bang. These discoveries were seen by many in the astrophysics community as having the potential to force the reinvention of cosmology. Professor Gupta's paper revives a nearly 100-year-old tired light theory and let it coexist with the expanding universe theory to arrive at its real age. In a sense, he reinterprets the red shift, or the light stretched by the expanding universe, into the red end of the electromagnetic spectrum as a hybrid phenomenon rather than due purely to the expansion. Professor Gupta spoke to Mayanksha Reports to explain the physics of the age of the universe. Welcome to Mayanksha Reports, Professor Rajendra Gupta. It's a great pleasure to have you on.
Likewise, I'm very happy to be talking to you. I hope I can answer your question. I can't guarantee, but I will try.
Well, you've written that extraordinary paper. I'm sure I'll fall short of my question. So let's begin with the remarkable tired light hypothesis, which is at the heart of your paper.
Yeah.
I know what it is. I mean, I understand broadly and how it's making sort of a comeback after it was first proposed in 1929 by Fritz Zwicky.
Yeah.
Tell my viewers a bit about what tired light hypothesis is and why you turned partly to that.
Actually, tired light theory has been, as you said, it has been something which was proposed by Zwicky a long time ago. And the basis of that tired light theory is that they thought that the light traveling very large distances perhaps get tired, and the loss of energy of photons or light is proportional to the energy of the photon itself and the distance traveled. And based on that, and using the Hubble's law, which says that essentially recessional velocities, or so-called recessional velocities, he thought at that time, which Zwicky did not think it was recessional at that time, using the Hubble's law that says velocity is proportional to the distance and proportionality constant is h0, for example, the Hubble's constant, what we call it today. And he derived a relation between the distance and the photon energy loss. And that became known as the tired light theory. What happens that whether you take the expansion model or the tired light theory, in the limit of very small redshift, they all reduce to the same expression. So as a result, in the early days, the redshift of the galaxies measured, or galaxies which they could see in the telescope, were relatively nearby. Means Z was in the range of about 0.1 or less, in that kind of range. So as a result, this model, Zwicky's model, as well as the expansion model, they both fitted the data. But there were other problems which tired light could not explain. And those were like the Tolman surface brightness, and why all those things were not very dominant at that time. But another thing was, what is the mechanism of the energy loss? And mechanism of the energy loss at that time was thought as some kind of a scattering process, similar to Compton scattering or something. But if scattering happens, then the image will get blurred. But that was not found. The images were very sharp. So this is the reason the tired light was not considered very seriously, and it lost ground after the launch of Hubble telescope. Hubble telescope essentially led to mm, led us to see far distant galaxies. Z redshift we can go to about 2 or even higher, and more recently even higher redshift just by Hubble. And that means people could really see that the data which was available using Hubble was not fitted by the tired light. So tired light theory went on the sideline. Essentially, it was forgotten.
I see. So do I understand it right that both the expansion model as well as the tired light model do result in some measure of redshift? Uh,
Yes, yes, both
okay.
of them result in the redshift. As I right in
Yeah.
the beginning, I said the photons lose energy. They say due to the that is proportional to the photon energy itself. Loss of energy is proportional to the photon energy itself and the distance traveled. What is the mechanism that is not understood? Even today, I can only hypothesize. If you will ask me, what is the cause? I think is for the tired light. I cannot say what exact physics is based on what we know. But we don't know a lot of things. So
Right.
I say it is perhaps cosmic drag, similar to the drag on particle moving through a fluid with some viscosity. And there are viscous models. A lot of people talk about various things, you know. But the field itself, see, the field it has to be conservative.
Mhm.
Excuse me. Conservative fields. Excuse me, I got disturbed
No, that's
for
okay.
the phone coming in. Uh, the conservative fields are the one in which you don't lose energy. Means you enter the field, you may change in the energy, but when you leave the field, you regain that energy. But if even if smallest component of that field is lossy component, you might say, then you will lose energy. So it doesn't require a lot of lossy component when you are traveling such a large distances, for the energy to get lost. So I feel there may be some way that the photon lose energy, not through scattering. No.
I see. I see. This is again, I'm digressing a bit. Say, for the sake of argument, the tired light theory had prevailed completely. Would that then mean that the universe is necessarily static? It's the tired light redshift that's the reality.
That's right. That's the prevailing concept at the time when Einstein developed his theory, that the light was, I mean, the universe was a steady state, and it was always the same, what they used to call perfect cosmological principle. Perfect cosmological principle mean not it is the same everywhere, but every time it is the same.
Right.
So this is, see, from anywhere, anytime, it should look the same.
Right.
Today we say it is the same, look from anywhere it is the same, but it is evolves with time.
Okay. Your paper explores if a hybrid between tired light and an expanding universe can resolve the impossible early galaxy problem thrown up by the James Webb Space Telescope. I mean, it's a remarkable combination that you come up with. Tell me a little more about it in a way that some of my ordinary readers and viewers would understand.
Yeah, actually, what I have done is not really something very new. If you recall, at the time, in the 17th century, Newton proposed corpuscular theory of light to explain his observations or observations of that time. And it prevailed in the 18th century. However, it could not explain diffraction pattern of monochromatic light, which were observed in the 19th century. But the corpuscular theory was then replaced with the wave theory of light. However, wave theory could not explain the photoelectric effect, which was observed in the later part of the 19th century and early part of the 20th century. Einstein then invoked the particle concept of light that was inspired by the Planck's work, and he then explained the photoelectric effect. So essentially, he brought back the corpuscular idea, but that doesn't mean that wave theory was not there. So eventually, people accepted that the photon or light has both the properties, particle property or corpuscular property, which Newton proposed, as well as the wave. And eventually we know now every particle has wave-like property as well as the particle-like property. So, what I have proposed is something similar. What I have done is I saw some paper which explained very well some of the observations of the James Webb telescope on resolving impossible early galaxy problem, and especially the sizes of the galaxies. It took the sizes of the galaxies. What we see is really from here the angular size of the galaxies. We don't see what their physical sizes are. And angular sizes are then converted into physical sizes based on the model. Now, if you use the Big Bang model, then these sizes turn out to be very, very, physical sizes are turning to be very small. Whereas when you convert those angular sizes using Light model, then they turn out to be reasonable. So the position is that yes, you observe these very massive galaxies. First problem is that how were they so early in the Big Bang created and so quickly, and they became similar in size and masses as, not size, because size they thought were very small according to the lambda model, but masses and shapes, all these were, and the frequency, the metallicities of some of the galaxies were similar to what we observe today. So how it happened so quickly? So this is the dilemma which was faced by the Big Bang model, but the size was explained by this tired light. So I read that paper, it was late last year, and that gives me an idea because I always thought about the tired light theory when I was very young at IIT Kanpur. I was thought about those things, but then I never worked on it. So I went back to that and say, maybe I can combine the two. So why not take the best of the two worlds, which explains the observations which Hubble telescope has at the, you might say, cosmic noon, that is what they call at redshift around 2 to 3 range and later, and also the other observation, which is the JWST at cosmic dawn. So if we combine the two, then we can explain both of these things and there will be no conflict. That was the inspiration I had.
I see. Within that context, you did talk about the impossible early galaxy problem. They were about 300 million years after the post-Big Bang. What about the Methuselah, the star, which is apparently 1 billion years older than the old age of the universe?
Yeah, these are the conflict things people have. They don't understand how a star can be older than the universe, but then they say maybe our models for star formation are not perfect. So they try to tune the star formation model. Similarly, when they couldn't explain the very large galaxy formation, they came up with the initial mass function, for example, for the formation of galaxies that is modified. The theories of the formation of stars and galaxies, they try to modify and then say, yes, if we modify these things, then it can fit the observed data.
I see. What was your first reaction when you first heard of the Webb images about the impossible early galaxy as well as the Methuselah star?
Actually, I wasn't sure about that. I thought maybe these things are very early observation and they might need some correction later on, which happens. And it did. In one of the galaxy, which was supposed to be at the redshift of about 16 or 17 in that range, it was eventually found to be at much lower redshift, about 4 or 5. So they were concerned, but at the same time, people eagerly waited for the confirmation. But many galaxies then did receive spectroscopic confirmation of these galaxies. And then we knew that a lot of galaxies were in the range of from 350 to 500 million years after the Big Bang. So how can they be created so rapidly? So people develop models to explain very quickly how it can happen. For example, some very large uh, primordial black holes were created and then sucked the material around it with super Eddington uh, rate. As a result, these supernovae were formed, and all these things happen very rapidly. Because even 300 million years or 500 million years is not very small time scale. It is still quite significant time scale. And very large stars, they live very short life. So if you can form population 3 stars, very large stars, the early stars, very quickly, if you can find a way of forming them very quickly, and you do have higher density at that time of matter compared to now when you are forming. So there are a lot of things which can be used to really produce these things, but I think not everybody is convinced about that thing.
Right.
Not me only. Means I have cited in my papers so many people who are skeptical about these kind of approaches which people have offered.
At what point did you begin to consider the idea of revising the age of the universe?
Actually, I didn't revise the age of the universe. I combined the two models. And one of the way to combine is that the distance traveled by light is the same. Whether you use tired light or you use the expansion of the universe, the distance travel is the same. Or if you use even both, the distance is still the same. So this puts a constraint, and that way you have two models. One gives one distance, one has a formula for distance, another one has another formula or equation for a distance. Now you equate these two distances, they relate then their uh, redshifts in certain way. You might say one causes redshift Z tired light, another expansion of the universe causes, say, ZX. Okay, now this relationship, because distances are the same, it can provide a relationship between ZX and ZT tired light. So this way, you are not required to find another constant or another kind of parameters to fit the data. You don't require. This is the advantage of doing this way. Now, when I combine these things and I do the analysis like the normal models are done, I get that age. Okay, so it is not that I put that age in, it came out from the model.
Oh, fair enough. So, but what one reads around in regular press, and I'm always somewhat skeptical because more often than not, they are driven by the ordinary readership, their comprehension, etc. But the figure of 26.7 billion light years, which is almost double what we have been told for decades now, that specific figure I'm very interested in. If you don't mind giving us a flavor of how you calculate that.
See, okay, that for that to know is how is it calculated with the standard lambda CDM model.
Okay.
It is calculated based on extrapolating essentially the when the Big Bang might have occurred, which causes the expansion of the universe observed today. So you essentially, if you have observed an expansion of the universe today and it is accelerating at certain place, you can backtrack it and see when it started. That if something is expanding, then you have to know when did it start expanding. For example, you launch something in when we have fireworks. Fireworks are going into space and we see they are exploding. So you can see, okay, at this time they exploded and this is the way they are exploding in the sky. When they explode is very easy to calculate. So essentially, the expansion rate provides you trace it backward and you get the age of the universe. And that expansion rate essentially, in a very simplified term, it's not exactly, but approximately, just to explain the concept, is that the Hubble parameter, which is h is equal h0, Hubble parameter is the rate of expansion parameter. So it gives you rate of expansion in terms, it says kilometer per second per mega parsec, for example. That's the unit of it. Now you extrapolate it and you can get when the universe started. When you add another way of light to lose its energy, that means all of the expansion or all of the redshift is not due to the expansion. That means your H0 parameter becomes the Hubble constant parameter related to the expansion part gets reduced. If that reduces, that increases the H. That means if it is expanding much more slowly, that means it must have started much more earlier to reach at this stage. If it is expanding faster, then it must have started later. That's the basic concept.
Is it fair to say that the JWST findings may begin to shake up the core of the Big Bang theory? There are already very passionate steady staters even now. For instance, I mentioned in my email that I had spoken to Dr. Vikramasinghe, who was one of the associates with Fred Hoyle, the original founder of steady state theory. And you do write in your paper that you do refer to steady state theory in your paper. Is it fair to assume that there is at least some measure of reinstatement of that thinking?
I think, okay, what is the hybrid of an expansion universe and a steady state? It means this is more slowly expanding.
Right.
If you combine the two, you say one theory says it is expanding very fast, another we say no, and then you combine, then you get a slowly expanding universe. Yes, so it is a hybrid thing. But at the same time, lot of findings of the Big Bang will remain. There is no doubt about that. Whatever astrophysics has been developed there, most of the astrophysics is developed in the near observing the near universe, not too far universe, but near um, time universe. So all these things are still valid. So this doesn't disappear, just like Newton's law of physics. They don't disappear in the everyday life. But when you try to consider your GPS system, and GPS system has to correct according to general relativity theory of Einstein, otherwise soon you will lose your precision of the GPS.
Right.
So that's what kind of example I give, that yes, when you come to very some of the observation, like as I mentioned, Hubble telescope, when it was launched, then it changed lot of things, our perception of the universe. It doesn't it put the Big Bang on a firmer footing than before. Then before that, the age of the universe, when Hubble found the recession of galaxies, it was 2 billion years.
Right.
And before the Hubble, it was between 7 and 20 billion years. Hubble then crystallized it to 13.8 billion years. Fine. Now, when we go back and analyze based on JWST data, we find that this is not really easily explainable with the that kind of age. Perhaps it is much better explained with the. I mean, it has more room to
Right.
explain. It's not only, see, you have 26.7 billion years, and you say it is about double of that. But during the early time, when the redshift was only about 10 or 15, at the time of 10, the uh, age of that time was 10 times more than that of the lambda CDM model. So you have, instead of 300 million years or 350, 400 million years available, you have about 5 billion years available for forming the galaxies. That's a lot of time to be able to create your galaxies and make them mature.
I see.
So it is more than double. Double is today, but really a whole lot bigger at a higher at the earlier times. This
I'm,
is
I'm
also
going to
shown in my paper.
I'm going to propose something which might sound ridiculous, silly, but I'm going to do it anyway.
Please do.
Decades ago, I had interviewed Dr. Jayan Narlikar
Yes,
in India. And my sense from him talking about the steady state was that even if the Big Bang, ironically, the Big Bang was coined as a mocking term by Fred Hoyle himself.
of
Yeah.
course, yes.
So my point, I mean, what I understood from that conversation was that the universe has always been around. The Big Bang was a mere local phenomenon which goes on. Is that a reasonable way to look at this at all?
See, I think one could see it in different ways.
Okay.
One is Big Bang. Big Bang is extrapolation of what we know. And then we say, okay, the element we observe, how were they created? And that's where the particle physics start coming. You extrapolate to the extent to the very high densities, and then you say, okay, how do we get the elements? Are they being created the ways in steady state theory they are created, or they are being created all at once at one point in time? So according to Jant, Narlikar, and Hoyle, they are continuously being created. According to the Big Bang theory, no, they were all created simultaneously. And there may be a possibility that people say maybe it is going through the phases of expansion and contraction and expansion and contraction, and that's what we are observing. And that could be as well, pulsating universe, you might say. So there are so many things. All we know, based on the observation, what people do, they create the best possible model to explain the observation. And when we have some new observation, then we try to fit them, and then we may have to modify. This is a continuous evolving process in science.
Right. You know, Roger, speaking of all that, Roger Penrose has been really pushing the conformal cyclic cosmology, much
Yes.
to the chagrin of many physicists. In fact, he has gone on record saying it is a bit more like Hindu philosophy. These are his exact words. I'm not the type who gets excited about these assertions, especially in the nationalistic India now. But this is coming from a very serious, very highly regarded physicist of the caliber of Roger Penrose, where he says the universe seems to go through cycles of some kind. Our universe is what I call an eon in an endless sequence of eons. Now, that sounds extraordinarily like what we grew up listening to in India, don't you think?
Yes, I think it is. But see, these things are more conjectures. Means what is the proof we have for that? The thing is this: in science we try to find the simplest solution possible, and this is we can always have lot of things. We might say it might happen this way, it might have happened that way, but unless we have a proof for that, it is very difficult to say which way or the other. All we can say, based on this, we can only say what the expansion phase we have today, and we how far we can extrapolate. Maybe we are extrapolating is too much, because when we talk about inflation and all that, that itself is a something not very convincing to a lot of people. But up to the point of inflation, for example, you can extrapolate and see, yeah, it explains what we have. But what happened beyond that? Maybe it was cyclic, as
I see.
Penrose suggested, or it was suggested by many other people. Yes, it could be. But we cannot go beyond. If we can find, okay, you have a signature of that from the past, and we can prove that it is from the past, then you can say. But if all the things from the past have been erased by creating
Right.
extremely high dense matter, then it is just a conjecture.
That's true. Then how about this? Given the astounding complexity of this universe, why couldn't it be that all of these, what we are saying, are true in some sense, somewhere, at some point?
I think all these things, again, I would cite the same thing. Anytime in science we say something happened, it should be proved in some way or the other, not just leaving as a conjecture. For
Right.
example, Dirac, based on his large number hypothesis, predicted the variation of the speed of light and of the fine structure constant or some other things and all that. And people try to verify their variation, because this was just a hypothesis, and nobody can prove that they are varying, because they tried to do it and they found that they constrained their variation through laser landing to about a 1 part in 10 to the power minus 15, to 1 part in 10 to the power 15, that it is not varying. Now, I have shown, this is another thing I want to bring here. I have shown that the constants I'm inspired by in this paper itself, I talk about the covariant coupling constant, that's why CCC. So these coupling constants are, I say, if they are all varying, and according to Uzan, who is a very famous physicist of current time, he has said that if one varies, then others must vary as well, and they should be a related variation of each other. Anyway, inspired by that, I come up with this thing theory. If I had slides to show, I would have shown you that better. But at the same time, based on the energy conservation and based on dimensional analysis, we can say the constants vary simultaneously. And if you constrain the variation of one, you constrain of all others. So what people do when they are seeing the variation of G, gravitational constant, they are keeping all the other constant. I so naturally in this way, how can they see the variation of the gravitational constant when they are constraining the speed of light to be constant because they have to vary in a correlated way. So this is another thing which and this is the basis of my uh, derivation of the equations in there, you know.
How has been the response of your fraternity to this remarkable idea about the age of the universe? What's been the response so far?
I think if I were the fraternity, I will be very skeptical. So naturally, people are skeptical. And what I have been trying to do, because this is a very elementary stage of this um, work,
Right.
and I never expected that I would get this kind of media coverage or of this. Like I have more than 30 videos that have been produced for this, and there were about 135, 150 um, press releases and other coverages which are there. I never expected. I thought, okay, some people will notice it. That's fine. It's great. It's just like any other paper. But one thing is good. Good media coverage does help me finding the critics of it, people like you who would want to discuss. And one of the things is this criticisms are the best thing to improve a
Right.
model,
Yeah.
not the pat in the back. It doesn't help. What helps is the critics.
Yeah.
So I am looking for all the critics which are there so I can respond to them and provide the uh, find an answer if I can. Or it is quite possible. It is quite possible. It is wrong. It
Right.
just fits some of the data, but rest of the data is doesn't fit.
Yes.
Recently, I must say, I should say that it does not really. Just 1 second. I have
Yeah.
to check something.
Please.
My battery might be a little bit low. So if it run out, then I'll have to connect to the battery.
Okay.
But I think for now it is
Yeah.
okay. Okay, let's continue.
Yeah.
Okay.
No, I'm saying I'm surprised that you did not expect this kind of media response for the simple reason that when you say that the age of the universe is almost twice as what we know, which would mean that at the stage of evolution that we are now, imagine 13.8 billion to 26.7 billion. We are so far away from the age of the universe at this stage. That means so many other things would have evolved over these many billion years, possibly even intelligent civilizations, which evolved and died out. See, these are the things that people think about when you talk about the age having been doubled.
Yeah, actually, this thing could have happened even in 13.8 billion years.
True.
Because after all, our solar system is only less than 5 billion years old. So
Yeah, but
really, it could have happened.
no, but it's 5 in 13 to 5 in 26. It's a fairly big difference, isn't there?
That's right. Instead of three times it more
Yes.
civilizations happening, it could have been happened 5 times. But that's all. It's not a big deal, you know.
Speaking of which, as a serious physicist, do you wonder about themes like that? That there could have been more intelligent civilizations in a more expanded age of the universe before us.
Again, being a scientist and not a storyteller, I would say unless I have a proof, I cannot say about it. But at the same time, I cannot deny it either because if you consider the perfect or even cosmological principle that we are not unique in this universe, our position is not unique in the position. So to say that we are the only civilization which ever happened seems to be a stretch.
Right. At this stage, where do you come? I know it's rather simplistic to ask a serious physicist this, but at this stage, where do you come down on the Big Bang versus steady state debate?
As I said, Big Bang and steady state debate, we have to combine the two.
Okay.
There are two things are at the moment it appears to be they are not one or the other. Perhaps they are the two sides of the same coin. So that, but coin is has both together, not one or the other.
Right. Uh,
Similarly, as I said about the photon, you have particle as well as wave behavior of the photon or other particles.
it would be fascinating to think what Fred Hoyle would say to what you just said, because he was reviled toward the end of his life for talking about. In fact, there are people who still ridicule him for the steady state theory, which I find strange. I don't know why people have such visceral reaction to that.
Yeah, actually, this is one of the thing, and I personally feel that it is very difficult to take one side or the other easily in cosmology because this is based on observation. You cannot do controlled experiments, only observations. So, based on observation, you might say the proof favors this side or the other side. And I think that's all what we can say. And in this way, I want to add, for example, you say about the criticism, I want to complete that side that already we have done additional work beyond the paper, which shows it confirms the at least part of the cosmic microwave background thing, as well as the baryonic acoustic oscillation, which is another very important factor. We find they are confirmed with the new model. I just wanted to say
I see.
something new in your talk beyond
Right.
what is in the paper.
No, that's interesting. Are you continuing to track what the JWST produces? Because they are saying that it's going to rewrite textbooks the way it's coming up with discoveries.
Actually, I wouldn't say it will write the textbook. A lot of material is still is the same. As I say, Newton's laws don't change. They are still there for everyday things. Yes, there will be something at the frontier of knowledge that will change, but the basic knowledge which is in the textbook may not change that much. But even textbook, we know we change certain things all the time. So certain things will have to be included. The quantum mechanics was not there. You were classical mechanics only, and when quantum mechanics came, then it became part of the mainstream curriculum. Not so. I think these are the kind of evolutionary things which will happen
I see.
anyway.
And finally, before I let you go, I regularly engage Dr. Abhay Ashtekar, the pioneer
Yes,
of loop quantum gravity, a
yes, yes.
remarkable figure himself. And the question that I ask him, I'm going to ask you, given the kind of universe that we live in, why can't there be more than one operating system? What is the need to unify and create a grand unified theory? Why can't the universe have several operating systems?
Yeah, those kind of very, very difficult questions to answer, you know. There could be, you see, one of the thing is this, having simultaneously so many theories together makes life very difficult.
Yeah,
So you have to eventually, you propose a lot of things, and then you crystallize, or you bring it down to something concrete. So yes, you can definitely have several operating systems. But what is today? You remember how much how many of the word processors were available in the 90s
right.
when the computer came out, or late 80s and 90s, so many. And then eventually we are happy that now we have one only, major one, which everybody uses. So I think it becomes life very difficult if you have various theories people are trying to propose and all that. We have to eventually come to some conclusion.